Getting back to the meta-analysis, the goals of the meta-analysis are to answer questions such as what is the direction of the effect? That is, we have a phenomena, we have an IV and a DV. As you go from one level of the IV to the other, what is the direction of the effect on the DV? Does the DV go up? Does the DV go down? What is the size of the effect? And now we're talking about effect size. Is the effect consistent across studies? There are general reasons why this is the case or not, and that's very telling when you look at these reasons why they're consistent or not. You can combine the results quantitatively. That is, you can dump several studies into a bin, a theoretical bin together, and you can look at the results based on what this new category you created says, or you could just look at the entire field of studies that you have and make a general conclusion. And finally is to investigate heterogeneity. That is, to examine why there are different results among studies. What are the reasons for these different results? I mentioned combinable before. Now I need to really define that. We say that articles are combinable when you have more than one study that examines a single phenomenon, and that you look at different study characteristics and conclude that they are unlikely to affect the effect. So I'll give an example in just a minute, but combinable means that if we are going to dump all 100 studies into one bin together, one theoretical stat bin, and say that they're all the same study, that has benefits and that can help out. But it only has benefits if they really are combinable, and that is if they're really looking at the same phenomena. And whether or not the studies are done exactly the same or slightly differently may affect if they're combinable. And the only way to tell is to investigate the differences. Look at the different studies and look at the different data from those studies, their results, their methods, to try to determine if they are truly combinable with other studies. And of course, this is more subjective than objective, and this is where one of the major problems with meta-analyses occur. That is, if a meta-analysis that has been published will be questioned, it's mainly about the issue of combinability, whether or not we can say two studies that we're looking at are essentially the same. Let's take a look at this table to give a brief illustration of combinability. So I'm looking at the weighted effect sizes here, and then I can total them up, and then I can divide them by n and get an average weighted effect size, which is generally what we do in every meta-analysis. And the question is, are these studies combinable? Or are there differences that make these uncombinable, that they should not be placed in the same bin? And in fact, if we would investigate further, we would look at the methodology and see that the methodology of these studies is different. Smith and Merriweather used concurrent concurrent validity methods, and Jones and Johnson used predictive validity methods. And so that was a difference underlying many of the differences in these studies. And so perhaps we should not combine those four studies together and look at this mean correlation of the weighted effect size, because these studies are coming from different methodologies. And indeed, when we look at the weighted effect sizes, we see that the concurrent methodologies have a much stronger weighted effect size, and the predictive has an extremely variable effect size. Okay, so now we see that there are differences in the methodology of these studies. Smith is concurrent validity and Merriweather is concurrent validity, and Johnson and Jones use predictive validity methods. And we see that the concurrent validities, we only have 2 of them unfortunately, are relatively close to each other in distance. However, we see that Jones and Johnson, their weighted effect size, it has a great deal of validity, variability, 99 versus 8.9. So given that it's a different methodology, given that our 2 studies for concurrent validity are relatively close to each other, and given that our 2 predictive validity methods are far away and have a huge variability, we may want to decide to say that this is non-combinable. And you'll see exactly what I mean as we get to the big example. And here's the big example. It's a case study. IO psychologist is working for a manufacturing plant. The current employment test correlates 0.25 with job performance. It's a robust correlation for both predictive and concurrent studies. People are talking about a new test, and so the IO psychologist does a literature review and finds 4 studies using the new test. And so here are the 4 studies using the new test. So let's just go back for a second. IO psychologist, and so the current test he's using has a correlation of 0.25 with job performance. That is the employment test. You go in, you want a job, you go in, they give you the employment test, and then they score it, and based on the score they give you a job or reject you. And they do this because they know that there's a correlation between your score on the test and your performance on the job. And doing this saves money for the company because you're only hiring people that will do a good job. If people are talking about a new test, which may have a higher correlation than 0.25, then you may want to find it, because every time that correlation increases between your employment test and job performance, you're saving your company money. And in fact, if you work it out, you're saving them tens of thousands of dollars for each 1/100th of a correlation point. So you do a literature review and you find 4 tests. Smith, it's a correlation of 0.22, Jones, correlation 0.33, Johnson, 0.27, Merriweather, 0.18. And so remember, our current test has a correlation of 0.25. So if we just use a voting method, we can see that, and remember again, these are all tests of the new employment test, and how well the employment test predicts job performance in this industry. And so we could just use a voting method, and so if we do that, is 0.22 higher than 0.25? No, so it's not better. Is 0.33 higher than 0.25? Yes, so this test does seem to be better based on Jones. 0.27, is that higher or lower? Yes. 0.18, is that higher or lower? Lower. No. So basically they're split 50-50. From just looking at the effect sizes, and remember R is an effect size, looking at the effect sizes, we see that there's no better or worse set of results that says that this test is better than the one I'm using, or worse. They're split, on this voting method. So if you just like do a yes/no type of tabulation, you're going to stick with your old test because it's not clear if this new test is doing any better. But we could do one better than actually, looking at a voting method, and we could actually take the mean effect size. And if we do that, the mean effect size is 0.25. And so again, now we're saying, well, if we take the mean effect size of this new test, it's the same as the old test, so we shouldn't do anything. So the voting method and the mean effect size methods say that we shouldn't do anything. We should stick with our old test because this new test is just as good and not any better. However, the voting method and just calculating a mean is not anything like what you do when you do a meta-analysis. One of the basic things that we do in a meta-analysis is we look at sample size, because smaller samples have larger errors than larger samples, and so therefore smaller samples are less trustworthy than larger samples. And so we need to have some way of taking into account sample size when we're looking at effect size. And one easy way to do it is weight the effect size by the sample size, and you do that by multiplying. So we have Smith has 125 subjects and an R effect size of 0.22. We multiply those together. Jones has 300 subjects, 0.33, and we multiply them together, and so on and so on. 125 times 0.22 is 2.75. 300 times 0.33 is 99. 33 times 0.27 is 8.91. And 99 times 0.18 is 17.82. We add those up, and it gives us that. And then what we do is we divide by the sum of the n's. And so here we have the total number of subjects is 557. So we divide the sum of the weighted effect sizes by 557, and that gives us 0.275. And remember, the old correlation, or the correlation for the old test, is 0.25, and the average is 0.25 also. But once we weighted this, we see that the weighted effect size, the average weighted effect size, is doing better than our current test. Our current test is 0.25. This new test, the average weighted effect size is 0.275. So this is exactly what a meta-analysis is. You're basically looking at different studies and you're weighting them by the size of the sample. Because again, smaller sample sizes introduce more variability into the effect size, and so the effect size we see is less trustworthy. And for example, I believe we're going to see, let me go back and check. Yep. We're going to see that these two are predictive, and so Jones has 300 subjects and their correlation is their effect size is 0.33, and Johnson has 33 subjects and their effect size is 0.27. And which one of these, or let me clear this up, which one of these effect sizes, 30.33 or 0.27, is more trustworthy? And in fact, because of 300 subjects, the 0.33 is more trustworthy. And so given the choice of saying, well, is it just 0.27 and 0.33, average together? No, I would put more weight on 0.33 being the actual effect size, because Jones has more subjects, and so there's less variability or less error in prediction of this effect size. And we'll talk about that in a minute. So our first conclusion from this sample meta-analysis is weighting by the size of the study tells us that the new test will be better than the old. So we already know what to do. Based on this meta-analysis, we should switch over, and given like a large-sized national company and the normal turnover costs, I once calculated that this new correlation between the employment test and job performance would save the company about $500,000 a year, which is significant. But then what else can a meta-analysis do? And the answer is we can group studies based on variables or characteristics. And so I've been mentioning concurrent and predictive validity. Concurrent validity is where you have a predictor, that is mental ability test, given to higher workers. And then what you do is you correlate that with their current job performance. This method has poor external validity because higher workers don't see this test the same way as job seekers. That is, when you're given an employment test as a job seeker, you're nervous, you're motivated, and so that's a very specific situation. When you're a worker and you're given a concurrent validity test, what happens is you're called into the IO psychologist's office, so you're getting time off work. Wow. And then you're taking a test, a paper test, which may be interesting, but it doesn't mean anything. It's not going to affect anything, so you're not motivated. So workers that are not motivated and they're not anxious like the job seekers, so there's poor external validity there. Predictive validity is when you take a predictor, that is a mental ability test, and you give it to job applicants. And then you hire all the job applicants, and then a couple months later you look at their job performance and see if there's a correlation between the predictor and job performance. And this has great external validity, and managers hate this because you have to hire everybody, and they're like, wait, we're giving them a job test, and then we're hiring them no matter how bad they score. That doesn't make sense. Well, that's why they hate it. But these are the two methods that we could use to generate validity data in an IO setting. And so we can expand our little table here like this by looking at, and this is what I showed you before, we could group the studies by predictive and concurrent validity. And so the concurrent validity studies, they have found that the average mean correlation, or the average mean effect correlation or effect size, is 0.20. And remember, the test that we're using right now is 0.25. So these concurrent studies are telling us that this new test is worse than the one we're using now. However, when we look at predictive studies, we see that the average mean correlation is 0.32, which is much higher than the entire data set and much higher than the test that we're using now, so it would be a great test to use. And we can take that information and feed it back into our understanding of the difference here. That is, predictive validity has better external validity than concurrent validity. So it could be that the concurrent validity studies are being affected by the poor external validity of having people currently at a job taking the test and goofing off during the test and not taking it seriously. Whereas in a very realistic situation, we find a much higher correlation between that new employment test and job performance. So conclusion number 2, predictive studies with better external validity have higher correlation than concurrent studies. And so that's the second thing meta-analyses can do. They can look at different types of studies. And in this case, it's IO-Psych, so we're looking at IO-Psych stuff. But in meta-analyses I look at, they're looking at things such as date rape versus stranger rape, or in things like that. So you can classify studies in different ways. You can classify them in terms of when they were conducted during the 70s, 80s, 90s, OOs, the 10s. So there's all different ways that you can classify studies and do a meta-analysis to tell you if there's any effect of whatever you're talking about affecting the relationship between the IV and the DV. And then finally, meta-analyses can do something very important and expose a major research problem. This is known as the file drawer effect. The file drawer effect basically says this. First off, only significant studies get published. And I've talked about this, and I'll talk more about this next week. So only significant studies get published. Only studies which find an effect get published. That's just another way of saying only significant studies get published. Non-significant studies do not get published, and they're filed away in file drawers in labs. And I have like 8 or 9 studies that found no effect that are sitting on defensive attribution, and they're sitting in file drawers in my office, except that during the pandemic there was a flood in the psych department labs, and I think everything was destroyed. I don't know, I haven't been back to campus yet. But the file drawer problem is pretty interesting because, for example, here we have studies that were published, and the numbers I give you certainly indicate that they were published, but then there could be a whole set of non-significant low effect size studies out there on this new IO test that are just sitting in file drawers because they're not going to be published. So let's give that a shot. And so here's what we do. Here's our original set of studies, and these were all published. And then what I do during my meta-analysis is I try to find all of the published and unpublished studies. And so first, York College in York, Pennsylvania, their IO psychologist there published a study on this new test, and she had 100 workers in her experiment, and the correlation she found between the new test and job performance was 0.02. And I ran into her at a conference, and we were talking about this, and she said, "Oh yeah, I have something in my file drawer that was non-significant that I didn't publish." Leo Sammy Incorporated, a big marketing research firm, they did a study with 280 subjects, and they found 0.11 correlation, and they didn't publish it because they're in business and they're not going to share it with other people for free. But a friend of mine got a hold of it and passed it on to me. York University in Britain did a study. One of the researchers there did a study with only 35 workers, and they found a 0.32 correlation. And finally, the Wilson Group, which is a group that I used to work with, not really, but it was a small consulting firm. They did a study on this new test with 68 subjects and found a correlation of 0.09. And so what we've done is we've looked at a special type of difference. Are they published or are they not? And so now we can make conclusions about, well, what's going on if something is published or not. Well, as we said before, the average weighted correlation is 0.27 or 0.28 for this new test. And that certainly says use it because it will save my company money. However, that doesn't take into account all the studies that had non-significant results. And so when you do that, the weighted average correlation is 0.1, and that is a really frowny face because that is much, much lower than 0.25, which is what the current test does. And then when we dump everything in together and say, okay, given the fact that we have these file drawer studies that weren't published, and we have these published studies, what's the average mean what's the average mean correlation for everything that we have? And look at that, 0.19. That's less than 0.25. So all things considered, we should not move to this new employment test because it does a worse job of predicting who will be a success and who will be a failure. And looking at the a file drawer effect is one of the beautiful things about a meta-analysis. Oh, okay, I want to skip this. So let's skip this.